Today we will talk about unlikely intersections in multiplicative groups and the Zilber conjecture.
Thank you very much. So, as anticipated, I shall describe some results that I yesterday have only very vaguely stated. Some results occurring in the algebraic groups Gm to the n. Yeah, no, just Gm to the n, by which I simply mean so and let me recall before stating anything the structure of the algebraic subgroups. Any such subgroup G, say of dimension R. Excuse me? Excuse me?
What is the E?
This one is the affine line. Affine line deprived of the origin. So this is an equality as varieties, and the group structure is the obvious one component with component-wise multiplication. So if G is an algebraic subgroup of dimension R, then this G may be defined by n minus R equations of the shape so here the AIs are integers, not all 0, and the dimension of something defined by this number of these equations is just R, provided just the vectors occurring as exponents are linearly independent. So saying that a point lies in an algebraic subgroup of this dimension simply means that the coordinates of these points satisfy n minus R multiplicative relations of dependence. Okay, this is just what I just wanted to recall. And let me now go back to the statement of Lang, to the problem of Lang that yesterday I mentioned as somewhat a prototype for the topic to be discussed. So Lang asked about plane curves. Say this equation defines a curve x, which I think is embedded in Gm2. And he asked about the points on the curve with whose coordinates are roots of unity, so torsion points. And the statement that he foresaw was that the curve contains an infinity of torsion points only if it is irreducible, only if it is a torsion coset. So this means just a translate of an algebraic subgroup by a torsion point. So by this description, the statement of Lang can be rephrased that X contains infinitely many torsion points if and only if it is a torsion coset, and which means that it is defined by some equation of this shape with this rho a root of unity. Let me give a very brief sketch. This is of a nice proof found, I think, by Serre. Lange attributes the first proofs of this statement to Ihara, Serre, and Tate, and I believe that the argument he gives is due to Serre. I don't know if the other ones were similar. Anyway, I just give this simple argument also because it contains some features that occur also in deeper developments. And the argument is simply this. So say that a point P lies on X. The curve X, we may think it is defined over the algebraic numbers, because if it contains an infinity of algebraic, the Riski-Denk set of algebraic points, then we may assume it is defined over a number field. And then we can take, let K be a field of definition, a number field of definition for X. And we operate on this situation with the Galois group. With we take a sigma in the Galois group of Q bar over K. So sigma fixes the curve and moves the point to a point P sigma, which also shall lie in X. But now comes the fact that P is a torsion point. And so P sigma, and the automorphism raises the roots of unity to a power. Say that this power is L. So we have that P to the L also lies in X, where L is associated to sigma. And this is, of course, means component-wise, taking the power component-wise. Okay, so on the other hand, this P to the L also lies in the curve that I am denoting now with this symbol. It means simply the curve which is obtained by raising the points of X to the power, to the nth power, which is an algebraic operation. So this is another curve. So we find a point in both curves. And now again, operating with the conjugates, we see that all the conjugates of P satisfy this property, so that P to the L lies in X and also in L times X. So we have, how many conjugates do we have? We have the number of distinct conjugates of P is just the degree of P over K. This is the number of conjugates. And now two things can occur. So we have these points lie on both curves. So the curve X is supposed to be irreducible, and the same holds for this. Either the curves are equal, and this is a first situation. And the second situation is that they are not equal, but then their intersection can be controlled by Bezout theorem and has at most the product of the degrees as a number of points. So in the second situation, we have at least these points on the curve. and we find this inequality. And well, this degree is fixed, and this degree may be estimated by L times the degree of x, since we are in 2 dimensions. So here we have this inequality times L. Okay, and now, of course, this degree, what is this degree? The point is a torsion point, and the degree shall be the degree of a root of unity of whose order is the common order, is the order of P. So this degree is bounded below by the value of the Euler function on this common order, which I denote by n, over the degree over Q of the field of definition, which is fixed. It depends only on the curve. And so now the proof, now we want to go into this alternative, because if we are in this alternative, I don't give the proof, but there are many ways to show that the curve must be of the shape that we are aiming, that we are thinking of. So we want to go here, and we want to exclude this inequality. So it suffices now to find sigma such that this L is small compared to the order of the point. But now we can prescribe any value practical to L, any value which is coprime to n. And so now very simple estimates from prime numbers, but not, we don't even need the Chebyshev bounds. Very simple arguments show that we may find an L which is coprime to n, and which is very small compared to n. So these bounds will contradict and give the solution. So I gave this argument. I find it's been nice, and also, as I told, this idea of taking the conjugates occurs in many of the arguments in all of this stuff. Let me say that Hindri in 1988 adopted the same kind of idea, so showing that it is a powerful one, to prove a quantitative Manin-Mumford conjecture. So after Renault's proof, this was quantified by Hindri using just this argument. Of course, he had to add additional deep ingredients. For instance, Manin-Mumford deals with abelian varieties, so there the Galois structure of the torsion points is much more mysterious. He had to use a deep theorem of Serre, giving the existence of homotheties, suitable homotheties in the Galois group. But so this was a very deep ingredient, but the philosophy of the argument is very similar to this one. So let me now state, so this result was soon Lange conjectured the general form of this result, and it was proved by Michel Laurent and independently Peter Sarnak. And then other proofs came by Liardet, I believe. And there are quite a number of proofs. So let me state this theorem. I may call it torsion points theorem. may be stated in this shape. The Zariski closure of a set of torsion points in Gm to the n is a finite union of torsion cosets. So this is a rephrasing, of course. If we have to already an algebraic variety x, and we want to describe the torsion points in x, well, we take the Zariski closure of them, which will be a subvariety of x, and it will be of this shape. So in particular, the torsion points shall be Zariski dense only if x, if it is irreducible, is itself a torsion coset. The proofs of this, well, several proofs can be given. For instance, the one of Sarnak, and I believe also Laurence had similar arguments, works on taking first describing fixed linear relations. So we assume the coefficients here are given, and Z1, Zm are roots of unity. And we want to describe the linear relations, and this may be done. For instance, there is the crucial lemma in Sarnak's that shows that the ratio, so if the number of terms is fixed and the coefficients are given, there is a ratio of two of the roots of unity whose order is bounded only in terms of m. And then this shows that practically this gives us a torsion coset out of finitely many. Then the general theorem is reduced to the linear relations just by viewing. So this the variety, we take the Zariski closure. This will be defined by algebraic equations, and we take one such equation, and so the monomials, we look at the monomials in this equation, and when evaluated at the torsion points, these monomials will become roots of unity, and we shall have a linear relations among roots of unity. And this is the idea. So after some work, one reaches that statement. So then so as I mentioned yesterday, the Lang conjecture about torsion points admits deeper conjectures related to the intersection of a variety with a group of finite rank, this case being the case of rank 0, of course. And this led also for abelian varieties, of course, to these conjectures contained the Mordell conjecture and were eventually proved by Faltings and in the abelian case, Voigt, I believe, in the semi-abelian, and Laurent in the multiplicative case. But I won't touch this development, and I shall consider another kind of generalization of the problems of Lang in the unlikely world. So let us take, again, we stay in the multiplicative group situation. We take a subvariety of Gm to the n. And so describing the torsion points on it is just this intersecting X with the algebraic groups of dimension 0. So in the spirit of this topic, the interest is also to intersect it with algebraic groups of whose dimension less than the complementary dimension. So let us define, make a simple definition. We define xd to be the union of the intersection of X with G, and G here is an algebraic group varying over all the algebraic groups with dimension D. So, and the previous case was, of course, D equals 0. So in 1999, in a paper with Bombieri and Massa, we considered the case of a curve. And we proved two kinds of results. So a first result concerned actually the likely intersection, as I said yesterday. So we took D equal n minus 1. So and for these intersections occur, there are infinitely many, but still one can say something, so namely a bound for the veil height under an assumption on X. So for this curve, the assumption that we made is that it is not contained in a proper algebraic coset. So in any algebraic coset of dimension n minus 1. And this means that the coordinate functions on X are multiplicatively independent modulo constants. So it is a stronger notion that not being it is an assumption slightly stronger. So under this assumption, we prove that X also we considered X defined over Q bar. We proved that this xd xn minus 1 is a set of bounded veil height. I recall here the height on Gm to the n, and we may choose, for instance, the sum of the heights of the coordinates, for instance. And so this result already asserts, for instance, that there are, which is not entirely clear a priori, that there are points. So if we take a point whose height exceeds this bound, and we evaluate the coordinate functions at these points, then the values remain multiplicatively independent. So it is a specialization theorem which says that the independence assumption is preserved except on a very sparse set. In fact, in particular, this implies that the points of bounded degree in x n minus 1 are a finite set, are finite in number. This immediately follows from Northcote's theorem. So this set had, this theorem had precursors. There was a theorem of Masser also predicting sparseness for this set, which was many years previously. And there is it may remind of a theorem of Silverman on elliptic curves, which also asserts bounded height for specializations where given independent points become dependent. And I shall discuss later the case of higher dimension of x, which is distinctly more difficult. And then I state the second result that we had. So under the same assumptions, the same result concerned just the unlikely intersection. So x is a curve, so we have unlikely intersections as soon as d does not exceed n minus 2. And in fact, already x n minus 2 is finite. And theorem 1 was an ingredient for theorem 2. And I shall discuss later, if time remains, this assumption of being not contained in a proper algebraic coset is necessary for theorem 1, but it was not clear that it was also necessary for theorem 2. And so for theorem 2, what is clear is that we have to assume that x is not contained in a proper torsion coset, which is an apparently small point, but in fact it leads to substantial difference. For instance, this theorem with coset replaced by torsion coset happens to contain the Lang's conjecture for intersection with finitely generated groups and groups of finite rank. Whereas if we apply this theorem in the version I have stated it, this is no more true. So it is not a small difference, and I will comment later again on this. So, and then some issues arose. There was the case, so here we assume that x is defined over q bar, and one can ask, of course, the same question for theorem 2. Theorem 1, we have the height, so we have algebraic points, but for theorem 2, it makes perfectly sense to ask about the finiteness also for a curve defined over an arbitrary curve defined over the complex. This we succeeded to prove in another paper, although with unexpected difficulties. We deduced the complex case by specialization. The philosophy is completely clear, but there are some technical difficulties due to the fact that specialization may collapse and infinite number could produce finite number after specialization. So this is just a technical point. And let me also say, as a previous theorem of this sort was already given by Schinzel in a completely different language in 1970, and about the case n equals 3. In fact, Schinzel then could use this result and apply it to his theory of irreducibility of lacunary polynomials. So using the general result, he was able to complete his theory. And I wish to sketch immediately the connection with this application. So Schinzel, for his application, had the following situation. He had two polynomials in n variables. And assume to be coprime. And then he needed to evaluate them by substituting for the variables powers of another variable t. So he considered these polynomials. So these polynomials now are polynomials in a single variable. Here what is varying are the exponents, the integer exponents. And for Schinzel's theory to go through, he needed to prove that except for special choices of the exponents, these polynomials remained coprime. And this was a consequence of not directly of this theorem, but of the methods used to prove it. We may see this as a problem of the sort that we are discussing in this way. So if the polynomials are not coprime, there is a common zero. And this zero lies, of course, in the codimension 2 algebraic set defined by P and Q. It is of codimension 2, they are coprime. And the fact that the variables are expressed in this form means that the point with these coordinates lies on a one-dimensional algebraic subgroup, the one parameterized by precisely this expression. So we are intersecting a variety of codimension 2 with an algebraic subgroup of dimension 1, and so we have an unlikely intersection, and this falls into this kind of things. Here we were able to prove this by the same ideas because essentially, so here x is a curve, and here, so dimension 1, whereas here the group has dimension 1. So these cases of complementary dimension admit the treatment on the same lines. Let me now speak.
N equals 3 sufficient for itself?
Yes, 1n equal 3, right. That it is directly. So an issue was of extending theorem 1 to x of higher dimension. We again had a result only for x of codimension 1. So again the same situation. But the cases of intermediate dimension were not clear, and actually it is one may prove that this assumption not to be contained in a proper coset is no more sufficient to derive a bound for the height. Let me give just a very simple example. We take in GM4, we take the surface defined by these pairs of relations. Here we may take another constant. for instance, this one. We take x defined by this. And now we intersect with the following algebraic subgroups. We take x to be a power of z, and we take y to be a power of w. And we have now the equation z to the m plus w to the n. W is 1 minus z, of course, equal 1. And now, since w is 1 minus z, well, there is a theorem of Zannier, a special case of minus, yes, minus 1 minus z. So I did the wrong thing, but it works also. The theorem of Zannier says that except for 2 points, if z and w are not roots of unity, the maximal height of z or w is bounded below by a positive constant. So if we take sufficiently large exponents, the height of x, and so there are points, but the height will be very large. And we shall obtain points in this surface, which lie on a codimension 2 algebraic subgroup and which arbitrarily large height, and still this surface is not contained in a proper algebraic coset. So an assumption, a different assumption, stronger assumption was needed, and we introduced the following the notion of so we started to think to unlikely objects of higher dimension. So what happens in this case is that this surface has the property that there is a family of algebraic cosets of dimension 2 which intersect it in a curve. So we have an unlikely intersection in a more general sense. It is the dimension of the intersection of x with these algebraic cosets is larger than expected. So this is in fact responsible for the failing of the analog of theorem 2. And x is covered by these things. It is easy to see. So we considered for a variety x the set which we denoted 0a, and the 0 came from previous work, and the a was referred, we called anomalous, this not rather than unlikely. And this set was defined precisely as x minus the union of, I call now unlikely intersections of positive dimension. By which I mean the intersections x intersected g such that the dimension of this is delta, positive delta, and the g is less or equal than the dimension of than n minus dimension of x plus delta minus 1. And and G here is a coset of an algebraic subgroup.
In this previous example, is this going to be, it could be empty?
It could be empty. And we proved again in joint work with Bombieri and Masser, we proved that this set is Zariski open. It is not entirely clear, and in fact there is even a more explicit description. One has to consider the maximal unlikely intersections to have a finite description, and then one can prove that, so here these are cosets, and the algebraic subgroup underlying the coset is taken from a finite set. So when one has this description, then it is clear that it is Zariski open. So with this, anyway, recently, Habegger has proved that the veil height in the anomalous part. So we take again x, a variety of dimension say d, and we now intersect with algebraic subgroups of codimension d, and we call we adopt the definition I gave previously, but only that we restrict to this set here. So the veil height here is bounded. So this was one development, and let me say that also concerning what I said earlier, that here, coming back to the case of curves, if we have here the assumption that is not contained in a proper algebraic coset, and we wanted to substitute this coset with torsion coset, and this was proved recently by Morin. For theorem 2, for the conclusion of theorem 2, it suffices that x is not in any proper torsion coset. And as I said, this contains the Lang conjecture for multiplicative case, intersections with, if it is suitably applied. And this theorem of Habegger, also showing the strength of it, actually if we combine with the methods that we previously had, allows a second proof of Morin's theorem, which should also be effective, by the way. This is object of very recent work with Habegger, Masser, and Bombieri. Okay, so now now, so so in this study, this study already of curves involves so already for the height involves these other unlikely objects, and we found that we found a few years ago that these unlikely intersection had been considered by Boris Zilber in a paper of his in 2002, who was interested in these things with completely different motivations coming from model theory. He was interested in constructing models of fields with an exponential function, namely a function which satisfies the addition formula of the exponential function. And he was trying to understand which are the right axioms for such a field, and in particular he had in mind the Schanuel conjecture, but he considered not only Schanuel conjecture, he had consideration which led him to formulate another conjecture which he used together with the Schanuel's one.
Maybe you can mention what is the Schanuel conjecture.
Yes, he had in mind the conjecture of Schanuel. So so we take n complex numbers, linearly independent over Q. And then the Schanuel conjecture bounds below the transcendence degree of the field generated by x1, xn, and the exponentials. This should be at least n plus 1. And this is a very deep conjecture. It amounts to a statement proved by Lindemann, I believe, when the x's are algebraic. And there are versions proved by X. Here's some version for function fields.
X1, xn are algebraic, then the transcendence degree is 10.
Yes. Yes. Thank you.
Just for big x1 equal 1.
Yeah. So Zilber had this, had this in mind, and had also the X version for function field, and he recognized the relevance of X in this context, and he stated a conjecture on unlikely intersections, of which he was able to prove a function field version by using the X result. So the conjecture of Zilber is the following one. So let X be a subvariety. Then there are finitely many algebraic subgroups of dimension at most n minus 1, such that if G is an algebraic subgroup and the dimension of then G is an irreducible algebraic subgroup. Then G is contained in the union of the T's. So this is, we may view it as a finite description of the unlikely intersections. The theorem that we had with Bombieri and Masser, the one, this theorem here, is a special case, but is the conjecture is much more difficult because of what I mentioned. Here we have algebraic subgroups, and whereas in the other one we have arbitrary cosets, and then mainly we considered only the intersection of positive dimension. So this amounts to a kind of function field version of this. So in the few minutes left, I mentioned, yes?
Zilber proved this in the function.
He has a version for function fields of this, yes.
Why?
Uh,
Say brief, you can say, just give an idea. Why are you using the function field that makes it easier there? I know with Model.
the fact that you can, yes, as happens often with function fields, we have derivations. And he was able to use, in fact, the X result, which is a version of the Shanuel in a differential field. And we also used derivation, however, in a different way with respect to Zilber. It is possible, well, Zilber, let me say, he gave very few details in the paper, and it is difficult to understand what he really had in mind. I think the thing has now been very recently worked out by a student of his. But I believe that there may be some common idea between this theorem and the function field version of Zilber's, but it should be inside the use of X. So because X used explicitly the derivatives. So in these last minutes, I mentioned a couple of other issues. For the case of abelian varieties, for instance, here there are papers of what's some name, Raymond, Viada, and others. The results are not as complete as in the case of in the multiplicative case, and this is largely due to the fact that in the multiplicative case, a crucial tool is a lower bound for the height of points of Lemmer type due to Amoroso and David in the multiplicative case, and this is not known in the abelian case except under, for instance, complex multiplications or other assumptions. So,
be more specific then. Is this a lower bound?
a lower bound, in the proof, we use the following theorem. So we let alpha 1, alpha r be algebraic numbers in a field of degree d over q. And we assume that they are multiplicatively independent. And we let epsilon. So epsilon should be given at the beginning, but so then there exists a number C depending only on epsilon and positive, such that the product of the heights of the alphas is at least actually their theorem is more precise because it gives here a certain function of d which is a power of log, but we apply it in the following shape.
C depends on R.
On R, yes. And yeah, it is. For R equal 1 is essentially due to Dobrovolsky. Is due to Dobrovolsky, yes. And it was the nearest approach to the Lemmer's conjecture, which in the case R equal 1 predicts here that we can throw away the epsilon. 0, yes. So, yes, this theorem was essential in our proofs.
And what were you saying about abelian varieties?
Yeah, no, in abelian varieties, there are yes. The same conjecture, by the way, Zilber made the conjecture also in that context. But we have, for instance, the analog of the theorem 2 that I stated is known only for CM abelian varieties, for instance, yes. And so another thing that but now my time is over, so I speak. No, there was another notion of dependence. Let me say just this. That in theorem 2 is somewhat, we need two relations of dependence to have finiteness. Whereas one would have a language in which if the functions are independent and the values are independent apart from a finite set. And Zhang found such a notion of dependence, which is an interesting one, and actually his notion is this one. He has functions, for instance, on a curve 2gm to the n, and he calls them dependent if there is a non-trivial multiplicative combination of the functions such that the image is a torsion variety. So he does not require that the combination is 1 or even constant. So he looks at the image. And with this notion, the theorem it may be rephrased and takes a more elegant, in my opinion, more elegant shape, because it becomes the statement that if functions are independent, then the values are independent except on a finite set. So, and now, so that's the end of my second lecture. Thank you.